Hello, everybody. I hope everything is going well with you guys. So, this is my lecture for week 10, session 1. Today, I will go over one example to design shell and tube heat exchangers. Then, I will go over design consideration for plate and frame heat exchanger, and then one example from plate and frame heat exchanger, and then we done this section, and then we can start the fluid mechanic part. So we already discussed the design considerations for shell and tube heat exchanger in my previous lecture. So in this example, we have benzene. This is a hot fluid with the inlet temperature now, known inlet temperature 51.7 centigrade, and then we use water as a cold fluid, with inlet temperature of 18.3. So we have the mass flow rate for both benzene and water, and then we have this shell and tube heat exchanger with the noun ID for the shell, and then some information for the tube and also the length. So also we have information for the uh, actually pitch size, and we know that this is triangular pitch and it has two passes. So then we know the number of baffles. There is actually 10 baffles, and you are asked to find the exit temperatures. And also, you are asked to just route benzene through the tubes and water through the shell. And so you have this information for thermophysical properties of benzene at two different temperatures. Okay, now to design each and every heat exchanger, as a first step, you need to find all thermophysical properties. So to find all thermophysical properties, you need to actually use a reference temperature. So for the reference temperature, you have actually three different options. So you can find all thermophysical properties, in the inlet temperature, or you can use an average temperature, because normally the inlet temperature of hot fluid and cold fluid are known. So you can use these two temperatures to find a T average, and then you can find all thermophysical properties at this temperature. And the third method, you can actually assume a value for exit temperature of cold fluid and hot fluid, and then you can find two different average temperature for the cold and hot side. So this is a typo, I should correct it. This is actually the TH average and the TC average. Now, so for this, problem, you can use, one of these, three methods. So, and then what you need to do after you need to solve the problem, you need to find the exit temperature, and then you need to find the new average temperatures. So, in the last step, you need to actually compare the T average, that you initially used to find the thermophysical properties, and the T average by using the exit temperature that you found in the last step. If the difference between these two average temperatures is less than 100 centigrade, you are good. You don't need to repeat the process. Otherwise, you need to actually redesign the heat exchanger by the new T average values. So in this actually problem we use 40.5 degrees centigrade as the average temperature for the benzene, and 22.2 as the average temperature for water. Then you can use you can find all thermophysical properties at this temperature. Again, guys, you can use any of those three methods to find the thermophysical properties. But what you need to do, you need to actually check this assumption at the in the last step after you found the exit temperature, to make sure that your assumption was valid. Okay. So based on this average temperature, you can find the thermophysical properties for benzene and water at this temperature. This is the first step to design each and every heat exchanger. So the second step, you need to find the flow areas. You need to find the information for internal diameters. For tubes. For the shell, and this thing. So to actually find the diameters, we know the inlet diameter of shell. This is known. This is available, in the information. For the tube, we know that we have this three-quarter OD13BWG tube. So if you use table 9.2, you can find the OD and ID of this, tubes. So this is the three-quarter, and then this is 13. So from here you can find the, ID and also OD. So based on table 9.2, ID tube is 1.42 centimeter and OD tube is 1.91 centimeter. So we have now the diameters for both shell and tube. So the next step, you need to find the D equivalent for shell. If you remember, we already discussed that to calculate the Nusselt number, you need to use the D equivalent for the shell side. So we need to find actually the D equivalent. And then if you remember, we had two different equations based on the tube actually configuration. So for the triangular pitch, you can use this equation to find the equivalent diameter. You need to have the SD is the pitch size. ODT, we found the ODT in the previous step. If you substitute the ST, ODT, and these things in this equation, you can find the equivalent. So this is the equivalent diameter for the shell. And then we need to find also the maximum number of tubes. If you remember from my previous lecture, the maximum number of tube depends on the several factors. Depends on the internal diameter of shell. It depends on the tube configuration. Depends on the pitch size. Depends on the OD tube. So if you use all this information and also table 9.3, you can find the maximum number of tubes. So we have this actually 17 quarter inches ID, and then we know that this is triangular 1 inches. So this is 1 inches triangular pitch, 3/4 OD, and then this is the 17 quarter, and then we know that there is actually 2 passes, correct? So if you use all this information, the ID, number of passes, and pitch size, you can find the maximum number of tubes. So the maximum number of tubes is 196. You need to know the number of tubes because you need to calculate the area, the heat transfer area. So you need to know the total number of tubes. Okay, now also you know that there are 10 baffles in this heat exchanger. So you can write L. L is the length of actually heat exchanger. This is equals to the B baffle spacing times NB plus 1. NB is the number of baffles, and then plus 1. So from here you can find B baffle spacing. So by using available information, the B baffle spacing is 0.445 meter. So also you need to find the clearance between adjacent tubes. Remember that we will use B, C to find the characteristic area and also the characteristic velocity. We already discussed that the area is not constant in the baffle, so we need to define a characteristic actually area and characteristic velocity to find the Reynolds number. So the clearance is actually clear area between two adjacent tubes. So based on this figure, you can see that this actually clear space equals to the ST or PT, which is the pitch size, minus the OD of tube. So we have all information. We have the PT, we have the OD tube, so we can find C. Now we have all information, to solve this problem. So this is the summary of first part. What we did in the first part, we just found the thermophysical properties, and then we found, some information for the tube size, for the shell size, number of tubes, baffle actually, uh, clearing, see, actually, the clearance between adjacent tubes, and also baffle spacing. So now, this is the first part. You are asked to find the exit temperature. So to find the exit temperature, you need to find the overall heat transfer coefficient. So to find the overall heat transfer coefficient, you need to have the heat transfer coefficient for both hot and cold fluids. So to find H, you need to find Nusselt number. So to find the Nusselt number, you need to find Reynolds number. So to find a Reynolds number, you need to find the velocities. So the next step to solve this problem, you need to find velocity. Why? Because you will use velocity to find the Reynolds number. Then from Reynolds number, you can find Nusselt number. From Nusselt number, you can find heat transfer coefficient. From the heat transfer coefficient, you can find overall heat transfer coefficient. And then from the overall heat transfer coefficient, you can find the exit temperatures. So to find the velocities, you need to have actually areas, the flow areas, correct? So to find the flow areas, because we actually use the flow areas to find both velocities and also to accommodate the fluids. In this problem, you know that the actually you already accommodate the fluids, but you can actually check that assumption. So to find the area for the tube, what you can do, you can actually calculate the area of one tube. This is the area of one tube, pi IDT squared over 4. This is the area of one tube. Then you need to multiply by the number of tubes, correct? To calculate, because you need to calculate the total area, for the tube. To calculate the total area, you need to multiply it by the total actual number of tubes, and then you need to divide it by number of passes. Correct. You need to multiply by number of passes. Why by the number of passes? Assume that you have just one pass. Correct. So all actually inlet fluid in the tube, just distribute, between all these tubes. Now, if you have two passes, assume that you have two passes. Correct. So what you need to do, this inlet fluid is distributed between 50% of these tubes, because 50% is inlet and 50% is actually 50% of the tubes are exit. So what you need to do to calculate the total area of flow area, you need to calculate the area of one tube. Then you need to multiply it by the number of tubes and then divide it by number of passes. So for the shell, you already saw that the area for the shell equals to the diameter of shell times C clearance times B baffle spacing over ST or pitch sizes. So we have all this information, everything is available. We already found all this information in the previous section. So here you can see the area for the tube, and then this is the area for shell. Again, this is the total area, for the tube, and this is the total flow area for shell side. Now, let's compare, the mass flow rate. This is the mass flow rate for benzene, and this is the mass flow rate for water. And you know that the fluid with higher mass flow rate flows through area, actually to section with the higher, area. So here, water has a higher surface, flow area, and then shell side has higher, flow area. So water flows through shell, and benzene flow through tubes. And you already know that, correct? So the assumption is correct. This is actually good, assumption to assume that the benzene, is in tube side, and water is in shell side. Now you have the area. You can simply calculate the velocities, and then from the velocities you can calculate the Reynolds number. So for the velocities, you can simply use the m dot and then density and the area to find the velocities. Here you can see the velocity for water and benzene. Now you have the velocities. You can find the actually Reynolds number. Just keep in your mind that for the tube side, the Reynolds number is velocity in the tube times IDT over mu. But for the shell side, you need to use the VS, correct? We already discussed in my previous lecture that velocity is not constant, so we can use this characteristic velocity. And you already determined this characteristic velocity in the previous section. And then you need to use the equivalent diameter, correct? To calculate the Nusselt number, you need to use the equivalent diameter. And we already determined the equivalent diameter. So you have everything. If you just substitute into this equation, you can find the Reynolds number. Then, by using the equation for the, Nusselt number, you can find the Nusselt number. Keep in your mind that here both actually two fluids are turbulent, and tube side and shell side. So by having the Nusselt number, you can simply find the heat transfer coefficient. Again, keep in your mind that for the tube side, you need to use the IDT to find the heat transfer coefficient, but for the water which flows in the shell side, you need to use the equivalent diameter. So by having the HO, if you assume that this is a new actually heat exchanger, then you can simply find the overall heat transfer coefficient. Now you found the overall heat transfer coefficient. There are two unknown temperatures, and you can simply find R, and then other parameters to find the exit temperatures. So if you remember from the previous lecture, R is the ratio of the m dot Cp for the cold fluid over the m dot Cp of warm fluid. You have all this information. You can find the m dot. Also, you need to find the heat transfer area. Keep in your mind that, guys, this heat transfer area is different from the previous area that you calculate. You calculate actually the flow area in the previous section for both shell and tube to find the velocity. This is the heat transfer, area. So the heat transfer area is the area for actually one tube times number of tubes. So this is pi ODTL, the area, the heat transfer area for one tube times number of tubes. So from here you have the R, and then to calculate S, you have two options, guys. You can use this equations to find S. So to use this equation, you need to have the C1, C2, and CT, and then C1, C2, and CT depends on the R. Overall heat transfer coefficient, heat transfer area, m dot Cp for the cold fluid. We already determined all these properties. All these parameters are known, and then you can find C1, C2, and C3, and also S. So by having this information, you can find exit temperature. Also, you can find S by using figure 913. So you can simply find the UA over m dot Cp and also R, and then from here you can find S. So by having the R and S and the definition of R and S, you can find the exit temperature. And this is the exit temperature. So the exit temperature is 26.3 for the cold fluid, and for the hot fluid is 28.9. Now, what you need to do, you need to just calculate the average, the new average temperature, and then compare this new average temperature with the initial value that you used to find the thermophysical properties. So if you calculate the new average temperature, for both hot and cold fluid, you will see that, the difference between this new average temperature and the initial value that you used to calculate to find the thermophysical properties is less than actually 50 degrees centigrade. You are good. You don't need to repeat calculations. So this is the first part. Actually, you found the exit temperature, but to design a shell and tube heat exchanger or any other heat exchanger, you need to check actually some other parameters. They are really important to make sure that your heat exchanger is working on a good condition. So one of these parameters, you need to check the heat transfer, the heat balance. You need to make sure that the QC equals to the QW equals to the Q. So if you use the information for if you use the information for warm fluid, cold fluid, and T2 and T1, the exit temperature that you found in the previous section, you can find the QW for cold and warm fluid, and you can see that they are equals. Also, you need to find the Q by LMTD method or NTU method. So I use LMTD method. I found F. We already discussed, how we can find F. And then I use this equation, Q equals to UAF LMTD. And I found that, the Q is 763.1 kilowatt. You can see that it's not equal to QC and QW, but I think I probably there is actually is a kind of error to find the F, because I use that figures to find F, so this value is not that much accurate, correct? So moreover, guys, the difference between this value and this QC and QW is less than 1%. It clearly shows that this F is not accurate. So you can claim that the QC equals to the QH equals to the Q, and this is acceptable for this case. Again, I probably this value for the F is not accurate, and this is why Q is a little bit different from this QW and QC, but it's not a big deal because the difference is less than 1%. Okay, so this is good. You are this green light in this part. There QC equals to QW equals to the Q. The other thing is that you need to check F. We already discussed it. You need to make sure that the F is higher than 0.75. If F is less than 0.75, then the heat exchanger operates in a costly mode. You need to just redesign the process, correct? You need to actually redesign the process, because this is not a good heat exchanger. So you need to play with the parameters. You need to increase the F. So to increase the F, F equals to the Q over U A LMTD. So to increase the F, what you can do, you can decrease the area, correct? If you decrease the area, then F increases. So you can actually play, with the parameter, probably with the area, to just decrease the area, to increase F, to make sure that, F is more than 0.75. So there is another green light here. So F is higher than 0.75. The last thing is that you need to check the pressure drop. And then you need to make sure that, the pressure drop is less than 70 kilopascal in both shell and tube side. So before that, you can also find the temperature after 1 year. How? By using the fouling factors. So if you assume that these are the fouling factors, and then you can actually find the new overall heat transfer coefficient, and then by using this overall heat transfer coefficient and repeat the process, we can find the new temperature, and then this is the new temperature after 1 year. If you compare this new temperature with the previous temperature, you can see that the exit temperature of hot fluid increases and the exit temperature of cold fluid decreases after 1 year. Clearly shows the performance, the actual efficiency of heat exchanger decreases because of the fouling factor. Okay, now pressure drop. So to find the pressure drop, we already discussed that you can use this equation to find the pressure drop, the total pressure drop in the tube side and in the shell side. So to find the pressure drop delta P, you need to find friction factor in both shell and tube side. So to find the friction factor, you need to find the Reynolds number. So the Reynolds number in the tube side, we already found it, and then you can assume that this is a smooth type. Or if you have any value for the relative roughness, you can substitute here. And then by using the Moody's diagram or any other correlation that you already learned in fluid mechanics, you can find FT. So the FT is 0.024. I have the Moody's diagram. We will go over that the Moody's diagram to find this. For the shell side, you can use this correlation to find the friction factor in the shell side. So for the tube side, this is almost the Reynolds number, 3 times 10 to 4, and then for the S-smooth tube, you can find the friction factor. So the value I found is 0.023, but the value by using correlation is 0.024. For sure, this value is more accurate than mine. By using the Moody's diagram. So this is the friction factor for tube side, and then you can use that correlation to find the friction factor in the shell side. You have all information, then you can simply find the total um, pressure drop in tube and shell side. And you can see that the total pressure drop in the tube is less than 70 and also in the shell side. So there is another green light here. So you have 3 green lights. You are good, and actually your heat exchanger works actually very good. So you are actually good in this part. So those temperatures are acceptable, the exit temperature. This is the summary for this example. Now look guys, I just prepare, this actually PowerPoint file to explain, the different steps. I also prepared this, Excel sheet file. And what you need to do, you need actually to use this Excel sheet, Excel sheet to design, each and every shell and tube heat exchanger. So I just, explain, different parts. So as a first step, you need to find the fluid properties, then tube sizes, shell data, flow area, and the other parts. So also, I just solve, that example step by step here. I'll just share, this Excel sheet. It's available on the Blackboard. So look, guys, I just substitute, the thermophysical properties for benzene and water at the reference temperature. So the second part, you need to find the tube and shell actually information, tube size, shell size, flow area, fluid velocities, and shell equivalent diameter. So the next step, we need to find the overall heat transfer coefficient. To find the overall heat transfer coefficient, first we need to find the flow areas, fluid velocities, and so the Reynolds number, Nusselt number, and then you can find the overall heat transfer coefficient. Also, you need to find the m dot Cp for the cold fluid and hot fluid, and also the minimum one. We'll use this information actually to find R in the next step. So then you can find the exit temperature. So this is the exit temperature. To find the exit temperature, you need to find the C1, C2, C3. I just explained it. And then this is the exit, temperatures. And then you need to just check the heat balance. So I just found the log mean temperature difference, and then Q. Here you have this green light, correct? And let's just make it green. Yeah, this F is less than 0.75. You are good, and then you have the QC, QH, and then temperatures after 1 year. To find the temperature after 1 year, you need to find the new U by using the fouling factor for both shell and tube. And then this is the temperature after 1 year, and then the last step, you need to find the pressure drop to make sure that the pressure drops are less than 70 kilopascals. Sorry, this is pressure. So yeah, what you need to do, guys, you need to actually report an Excel sheet and then include all this information in that Excel sheet. This is available on the Blackboard. And then okay, guys, now we can start chapter 10, design consideration for plate and frame heat exchanger. So this is chapter 10 of Journal textbook. So as an introduction, plate and frame heat exchanger, they were introduced in 1930, and then they normally use, in food industries. So actually, plate and frame heat exchanger consists of several metal sheet with corrugated surfaces. One of the actually important design parameters to design all plate and frame heat exchangers is the chevron angle, which is the angle between the adjacent ribs and the vertical. So actually these angles, in some textbook, this is called theta, in some other, beta. So this is really important because the higher beta means, the higher actually heat transfer, rate, and higher, actual surface area. And then, however, at the same time, the higher beta means, the higher pressure drop, or, pressure losses. So, yeah, here I actually share, several videos with you guys, about the, plate and frame heat exchangers. Let's watch one of these videos, and then you can guys go over, on other, YouTube's, at home, videos at home. So this is one actually, plate, and then we use this gasket to make sure that, the plate is sealed. And so here you can see, the fluid actually, accommodation. This is the cold fluid. And then you can see that, the cold fluid is distributed, over different, plates, correct? So one plate with the cold fluid, the other one with the hot fluid. Cold, hot, cold, hot. Then this is the hot fluid, right? And now you can see, the combination of both hot and cold fluid over the plate. Okay, now, so yeah, here we can see, a simple, actually a schematic for plate and frame heat exchanger. So this is the hot fluid. As you can see, it's just distributed, over different, plates. And then this is, the, cold fluid. And normally, all plate and frame heat exchanger work, the fluids are, counterflow. So here you can see, some actually advantages of plate and frame heat exchangers versus shell and tube heat exchanger. The first thing is that normally they have higher specific surface area or higher surface area per volume. So if you at a constant volume, if you need, higher heat transfer area, you should use, the plate and frame heat exchangers. Normally they have lower fouling, they have a smaller size for sure because they have higher a specific surface area. And then one of the actually a specification of a plate and frame heat exchanger is you can simply you know um, change the capacity of the heat exchanger. For example, you have this heat exchanger with the capacity of A, and then after 1 year, 2 year, 10 year, for some reason you need to add the heat transfer area. So what you can do, you can simply add some new plates to the heat exchanger, and then you can simply increase the heat transfer actually rate. So you can actually play with the capacity of these plate and frame heat exchangers. Here you can see the actually comparison between different plate and frame heat exchanger. This figure is from thermal design by Hussein Lee, and as you can see, the main parameter here is the specific surface area or heat transfer surface area density, or the surface area over volume. So you can see that if you need higher, plate, higher specific surface area, you need to use the plate heat exchanger. If you need more, actually, a specific surface area, then you need to use fin, a heat exchanger. You can use fin tube heat exchanger or plate fin heat exchangers. So you can use different actually flow arrangements for plate and frame heat exchanger. In this course normally we use the one pass flow system. This is the one pass flow system. You can use two pass flow system, or you can use two pass one pass flow systems. Materials. So the first thing is that to decrease the thermal resistance by conduction, normally we use thin, plates for the plate and frame heat exchangers. So normally the plate thickness is almost 0.6 millimeter. They are really thin. Steel is the most commonly used material. However, depending on the several factors, you can use other materials. For example, depending on the pH of your, for example, fluid, depending on the if the fluid is actually corrosive, or other parameters, temperatures. You can actually use different materials. So for example, for brackish water, you can use titanium as material. But keep in your mind that if you use titanium, and normally the thermal conductivity of titanium is low, it's almost 20 watt per meter Kelvin. Then just compare it for with the thermal conductivity of material, which are are normally more than 150 watt per meter Kelvin. Then you can see that the thermal conductivity of titanium is really low. And so yeah, you can use several other options. Here you can see some examples for materials. So the maximum working pressure actually depends on the frame strength, and normally the operating pressure is something between 85 psi to 300 psi. So for the maximum working temperature, the maximum working temperature depends on the gasket strength. Correct. So normally we use styrene as a gasket. So if you use a styrene, the maximum temperature is something around 70 centigrade. If you need higher temperature, if you have material fluids with a higher temperature, then you need to use other actual material. For example, you can use asbestos fiber as material for the gasket. So in this case, for example, if you use the asbestos, the maximum temperature can be something around 200 centigrade. So these are two limitations for plate heat exchangers. So to calculate the overall heat transfer coefficient, if you have a clean heat exchanger, if there is no clean heat exchanger, the first thing is that, which is really important, indeed, to calculate the overall heat transfer coefficient for the plate and frame heat exchanger, AI equals to the AO, because we have this simple, actually plate, correct? So the AI equals to the AO. If you remember, for shell and tube heat exchanger and for double pipe heat exchanger, AI is different from AO, but here in the plate and frame heat exchanger, AI equals to the AO. So if there is no actually, fouling factor, so the total thermal resistance is the thermal resistance by, hot fluid, cold fluid, and the conduction one. So the area is the area of one actually plate, which is the B times L. B is the width of the plate times L, length of the plate. And so yeah, AI equals to the AO, and then you can simply find the overall heat transfer coefficient, because you can cancel the area. Here AI equals the AO, you can simply cancel the area to find the overall heat transfer coefficient. For the dirty heat exchanger, you need to add the fouling factor. So you need to add two fouling factors here, R double prime, for the hot fluid, and R double prime fouling for cold fluid. So by having this information, you can find the overall heat transfer coefficient. It's a little bit actually, easier, from the shell and tube and, double pipe heat exchangers. So to find the fouling factor, we already discussed, you can use, the reference, sorry, the reference tables to find the overall heat transfer, the fouling factor. Now, hydrodynamic and equivalent diameter. We already discussed, to find the Nusselt number, you need to find the Reynolds number, and then for the Nusselt number, you need to find the Reynolds number based on the equivalent diameter. And then to find the Reynolds number, to calculate the friction factor, to calculate the, delta P, you need to use the hydraulic diameter. So for the plate heat exchanger, if we assume that the actually, I made a mistake here. I need to just fix it, guys. If we assume that the B is the width of, let's just crack it right now. So yeah. Yeah. This is actually B, and then this is the S. Yeah. So yeah, if we assume that the S is the distance between the two plates, assume that this is a two plate, for the plate and frame heat exchanger, and then B is the width of the plate, correct? We can use the definition for the, hydraulic and equivalent diameter. For example, for the hydraulic diameter, if you remember, the definition of the hydraulic is 4 times a flow area over P actually valid. So here the flow area is actually B times S, correct? Fluid flows, the in distance between the two plates. So this is B times S. So the P weighted is 2S plus 2B, this area, this, perimeter. Now, keep in your mind that normally the S, this distance between the two plates is much smaller than, the plate widths. So you can assume that B is actually much bigger than the S. So then if you just assume that B is much bigger than S, then you can actually, ignore this part, and then you can write the D hydraulic equals the 2S. If you use the definition for the equivalent diameter, and then again you assume that the B is much bigger than S, you will see that the D actually equivalent equals to the 2S. So from here, you can assume that actually you can conclude that the D hydraulic equals to the D equivalent for plate heat exchanger. So for the plate heat exchanger, there is only one, diameter. D hydraulic equals the D equivalent. So you just need to calculate one Reynolds number. Now, so the next part is the velocities. How we can find the velocities. Okay, look guys, this is a simple, a schematic for, plate and frame heat exchanger. Assume that, let's say, there are 5 plates, correct? Now, if you have 5 plates and this is the hot fluid, look, hot fluid actually flows over this plate, and this plate. So it actually uh, flow over 3 plates. So we have 5 plates, or we can say hot fluid actually flows over NS plus 1 over 2. NS is the number of, plates. So what's about the cold fluid? The cold fluid flows over this one, 2, and the plates over, and the backside of this one, correct? So 1, 2, and 3, plates. So for the cold fluid, you can also write, the actually fluid, the total, fluid is distributed over, 3 plates, or N plus 1 over 2. So what's the conclusion? The conclusion is that if you have odd number for the number of plates, for example, 5, so the fluid, actually the flow is distributed over, NS plus 1 over 2 plates, correct? So to find the velocity over each, on each, plate, you need to find the m dot, the mass flow rate on each, actually plate. So based on this explanation, the m dot for each plate, for both hot and cold fluid, if you have plate heat exchanger with the odd number of, plates, equals to m dot over ns plus 1 over 2. This is the m dot over each plate. If you combine these two equations, you can find the velocity for each, fluid. So the velocity for each fluid equals to the m dot over rho a times ns plus 1 over 2. And now you know what's the actual origin of this, ns plus 1 over 2. What happens if, we have actually even number of plates? If you have even number of plates, for example, assume that, we have 4 plates here. If we have 4 plates here, so for the hot fluid, flows over this one. This is 1, 2, and then the third one will be on the back side of the last one. So it's 3, correct? So this actually flows over, 3 plates, or over NS over, let's say, sorry, yeah, NS over 2 plus 1. Look, here we have 4, and then hot fluid flows over 3 plates, or NS 4 over 2, which is 2 plus 1, which will be 3. So if we have an even number of plates for one fluid, actually it's flow over NS over 2 plus 1, plate. For the other one, for the cold fluid, if we have, 4 plates, it flows over 1 and then 2, plates. So actually it flow over ns over 2 plates, or 2 plates, correct? So 4 over 2 is 2 plates. So for one plate, for actually one fluid, and m dot is distributed over ns number of plates over 2, and for the other one it's actually distributed over n over 2 plus 1, plates, correct? So we will have two different velocities, in this actually, two different, sorry, equations to find the velocities. And here you can see that for one fluid, you need to actually divide the m dot by ns over 2, and for the other one, you need to divide it by ns over 2 plus 1. And now you know the origin of these two velocities, actually, terms. So you can use this equation to find the velocity. So it depends on the number of, plates. If you have the odd number or even number of plates. So heat transfer coefficient. So to find the heat transfer coefficient, the first thing is that the definition of laminar and turbulent flow is different. Actually, not the definition. The critical Reynolds number is different. So for the plate and frame heat exchanger, the critical Reynolds number is 100. So if the Reynolds number is less than 100, the fluid flow is laminar. Otherwise, it's turbulent. So for the laminar flow, you can use this correlation to find the Nusselt number, and then here you can actually use the hydraulic diameter. I explain you guys the hydraulic diameter equals to the equivalent diameter for a laminar flow. So for the turbulent flow, if the Reynolds number is higher than 100, then you can use this correlation to find the Nusselt number, and then from the Nusselt number you can find hydraulic, you can find the heat transfer coefficient. Again, all these thermophysical properties required to find the Nusselt number are determined at T reference. Now, to find the Q by using, the LMTD method, you can write Q equals to the U, the overall heat transfer coefficient times the total area. The total area is the area of one plate times number of plates times F times log mean temperature difference for counterflow. So this area is, the area for the heat transfer, and this is actually B times O. And to find the correction factor, if you just check, the previous lecture, you have 4 figures in, tables, actually figures 11S1, 11S2, 3, and 4 from the, Bergman, textbook. So there is no, figure for plate and frame heat exchanger. So to find the correction factor for the plate and frame heat exchanger, you can use this equation to find the F. You don't have any, figure. So you need to have the NTU, and if you remember, the NTU is U, the total area over M dot CP mean. So, and the total area is the area of one plate time number of plates. So the log mean temperature difference, we already discussed it. You need to find the log mean temperature difference for counter flow. And also you can write, Q for the hot fluid and Q for the cold fluid. And then eventually you need to make sure that there is a, heat balance in the heat exchanger, meaning that QC equals the QH equals the Q by using the log mean temperature difference. So keep in your mind that, guys, F must be lower than 0.75. So you need to check F to make sure that F is less than 0.75. And then the last thing, you need to calculate the pressure drop, and you need to make sure that the pressure drop is less than 70 kilopascal for both two sections. So to find the pressure drop, you need to consider both major losses and minor losses. So for the major losses, the pressure drop over the plates. So you can actually use, this correlation. We already proved this equation, by using the Bernoulli equation. You can write delta P equals the FL density velocity square over D hydraulic times. So again, guys, D hydraulic equals the D equivalent for plate and frame heat exchangers. So F is the friction factor. So for the friction factor, don't use the Moody's chart. Why you don't, actually you can use the Moody's chart, because the Moody's chart, guys, is based on, the critical Reynolds number of, 2,200. But here, the critical Reynolds number is different. So for the Reynolds number between 1 to 10, use the first correlation, 10 to 100 the second one, and higher than 100, use the last equation to find the friction factor. L is the plate length, V is the velocity. We already discussed different methods to calculate the velocity. It depends on the number of plates. And then also you can calculate the delta P, for the port, actually, minor losses. So the major losses is, actually pressure drop over the plates, and the minor loss is, due to the expansion or contraction of the fluid in the inlet or exit. It depends to the, velocity in the port, and also depends on the diameter of the port. Keep in your mind that in most cases this delta P is negligible if you have a good design, in comparison with the other one. So if you add these two terms, you can find minor losses and major losses. You can find the total delta P. So for the temperatures, if you have one temperature, one unknown temperature, you can simply use the energy balance between the cold and hot fluid to find, the unknown temperature. If you have two unknown temperature, we already discussed it, you can write the energy balance for the cold fluid, energy balance for the hot fluid, and also Q equals the UA times NF log mean temperature difference. If you solve these three correlations simultaneously, you can actually find the T1 and T2. So to find the the exit temperatures, in this case, if you have two unknown temperatures, first you can find R by having the m dot Cp for the cold fluid and hot fluid. The ratio of these two is R. Then you can find the EC. To find the EC, you need to have the overall heat transfer coefficient, the overall area, F, correction factor, R, and m dot Cp for the cold fluid. And then using the definition of, by using this correlation, you can find the exit temperature of hot fluid. And then by using the definition of R, you can find the, exit temperature for the cold fluid. Here you can see, guys, the different actually steps to design a plate and frame heat exchanger. You need to find the thermophysical properties. You need to find the plate dimensions. You need to find the velocities. Then by having the velocities, you can find the Reynolds number, and then Nusselt number, the overall heat transfer coefficient, and then you can find the exit temperatures. Then you need to make sure that there is a heat balance in the heat exchanger, and then you can find, you can use the fouling factors to calculate the overall heat transfer coefficient and temperatures after, by using, the fouling factors. And then eventually you need to calculate the pressure drop, and you need to make sure that the pressure drop is less than 70 kilopascal. Okay, let's go over this example, guys, and then I will just explain all these details, in this example. Okay, so you're asked to design a plate and frame heat exchanger. You have the volumetric flow rate for EG, and also for water. So you have volumetric flow rate for both these two fluids. Also, we have the inlet temperature for EG, and also inlet temperature for water. We have the plate height, plate spacing, or S. Also, we know that there are 15 plates, and then we know the material, the stainless steel, so we can find the thermal conductivity. So we have the thickness for the plates, and also the width of, plates. You're asked to find the outlet temperature for both fluids. Also, you ask to just assume the fouling factor, this fouling factor for both two fluids. Here you can see this simple schematic, with all available information. So we have the information for hot fluid, volumetric flow rate, the inlet THI for the hot fluid, TCI for the cold fluid, and volumetric flow rate. Also, we have the L, we have the plate width, we have the spacing, between the two plate spacing, and also this is all information. So the first step to design each and every heat exchanger, you need to find the two reference, and then by using the two reference, you can find the all thermophysical properties. Here, actually, there are you have three options. I already explained it. The three different options to find the T reference. So in this case, if you look at the temperature, guys, look, the inlet temperature are pretty close. This is the 24 and the other one is 10. So they are pretty close. So what we can do, we can actually, find, all, thermophysical properties, at the inlet temperature. So we can use two, different actually temperatures. We can assume that the T average for, hot fluid is, the THI, and for the, cold fluid is TCI. This is, good assumption. So we just calculate all, thermophysical properties at for EG at 24, for ethylene glycol, and for water at 20. Again, guys, you can use any of these, three methods, and then you will see that, the thermophysical properties are very close, to these, properties. So or what you can do, you can actually use the these two inlet temperatures to find the average temperature, which is 34 over 2. It's something around 17. You can find 70. So, or what you can do, you can just use the and actually average temperature after several atoms to find the exact temperature. But if you use any of these three methods, you will see that the thermophysical properties are very close to these numbers. So this is the first part, the thermophysical properties. The second step, to design each and every heat exchanger, you need to find actually the flow areas. You need to find the uh, you know dimensions, for the tubes, shells, for the plates. Here, we have the plates, so we need to find, the dimensions. So we have some dimensions. We have the BLS, so we need to find two. We need to find the hydraulic and equivalent diameter. Correct. So we saw that the hydraulic diameter equals the equivalent diameter, and then by having the S, you can find the hydraulic. The second step, you need to find the surface areas and flow areas. So the surface area actually is the area for the heat transfer. So we use the A naught to find the actually to calculate the heat transfer rate. So A naught is actually B times L, the area for the heat transfer, the area for actually transfer for one plate. But the flow area is actually S times B. Look, actually fluid flows in this part. So it's the distance between two plates times plate widths. So by using B and S, you can find the flow area. So we have two different areas. So here we can see the summary of this part. So we have all dimensions. Also, you can find the thermal conductivity for which is 14.3 watt per meter Kelvin. Now, the next step, look guys, you need to find the exit temperature. So to find the exit temperature, you need to find the overall heat transfer coefficient. To find the overall heat transfer coefficient, you need to have HI and HO. To have the HI and HO, you need to find the Nusselt number. To find the Nusselt number, you need to have the Reynolds number. To find the Reynolds number, you need to find the velocity. For the velocity, we have two cases, depending on the number of plates. For the odd numbers, if you have, plates, actually plate and frame heat exchanger with the odd numbers, you can use this correlation for both two fluids. So the M dot is the M dot for the, fluid, and S is the number of plates, A is the, flow area, and rho is the density of fluid. So if you use this information, you can actually find, the velocity for ethylene glycol and water. So now we have the velocities. We already determined the hydraulic diameter, so we can find the Reynolds number for both two fluids. So the Reynolds number is 161 1, and for the ethylene glycol, and for water is 1984. So if you remember, guys, the critical Reynolds for plate and frame heat exchanger is 100. So Reynolds fluids with the Reynolds number more than this critical Reynolds number or more than 100 are turbulent. So both two fluids are turbulent based on this Reynolds number. So they are turbulent, and then you can use this correlation to find the a Nusselt number. So by having the Nusselt number and the definition for hydraulic diameter, also thermal conductivity for ethylene glycol and water, you can find the heat transfer coefficient for EG and water. Now you have the heat transfer coefficient, you can actually find the overall heat transfer coefficient. You have the fouling factors, you have the thickness of each plate, thermal conductivity of plate, and by using this information, you can find the overall heat transfer coefficient. So now you have the overall heat transfer coefficient. You can find the correction factor. So to find the correction factor is can use this correlation. You need to have the U. You find the U. You have the A naught, and as number of threads is 15. You need to find the M dot CP mean. So you need to find the M dot CP for both two fluids, and then from here you can see that the actually M dot CP mean equals the M dot CP for EG. So if you combine all this information, you can find the NTU, and then from the NTU you can find F. Look, guys, F is more than 0.75, so you are good. This heat exchanger, actually good. Yeah. So one green light here for the F. Then to find the exit temperatures, you need to find, you have actually that case with two unknown temperatures. So you need to find the R by using the M dot CP for cold fluid and hot fluid. You have this information, so you can find the R. Now you have the R, you need to find the EC. To find the EC, we already determined all, parameters. If you substitute here, you can find EC. So EC is 1.272. You have the EC. By using this definition, you can actually find the exit temperature of cold fluid. So the exit temperature of cold fluid is 16.7. And then by using the definition of R, you can find the exit temperature for the hot fluid. Sorry, for the cold fluid, my bad. So look, guys, now you found the exit temperature. Now you need to check your assumption. So if you use any of those three methods, you will see that your actually average temperature, the new average temperature by using this exit temperature for hot fluid and exit temperature for cold fluid is less than 15 centigrade. 15 centigrade. So your assumption is good. You don't need to repeat the calculation. But again, guys, if you design a heat exchanger and then you saw that the actually the new average temperature is more than 50 degrees centigrade, you need to actually redesign your heat exchanger by using the actually new average temperature and new thermophysical properties. Okay, so now for the next step, you need to actually calculate QC, QH, and Q, and then you need to make sure that there is a heat balance in the heat exchanger. So by using the available information, you can find, actually we can show that the QC, QH, and Q are equal. So there is a heat balance in heat exchanger. This is another green light. And then you need to calculate the pressure drop, and you need to make sure that the pressure drop is less than 50 kilopascal. So for the major losses, you need to find F. So to find the F, if you remember, it depends on the Reynolds number. So for both these two cases, the Reynolds number is more than 100, so you can use the third correlation to find the friction factor, for both ethylene glycol and water. This is water, guys. Another, typo, sorry. So, yeah, if you just use the velocities, the hydraulic diameter, and all this information, you can actually calculate the delta P for ethylene glycol and delta P for, water. And you can see, in these two cases, the delta P is lower than 70 kilopascal. If you compare, guys, this, delta P with those delta P that you always determine, for the, uh, double pipe heat exchanger and for shell and tube heat exchanger, you can see that the delta P is higher, in this case. So, and it's normal. For the minor losses, if you assume that the D in the D port is 0.05 meter, and then you calculate the LP, and then you calculate the velocity in the port for the water and ethylene glycol. You can calculate the velocities, and then you can find the delta P in actually the minor losses, and you can see that the delta P minor losses is negligible. So from here, you can actually use the major losses. You can report the major losses for both ethylene glycol and water, and then another green light. The delta P is less than 70 kilopascal, and this is acceptable. Please study example 10.1 before I finish this part, guys. Again, I prepare this, file to actually Excel sheet to design a plate and frame heat exchanger. This file includes, all different steps that you need to just follow to design the plate and frame heat exchanger. Also, I share, another file. This is, a step-by-step, procedure to solve, that example that I explain you. So you need to find the T reference, you need to report the thermophysical properties, you need to find the, plate dimensions. So yeah, two areas, the hydraulic, number of plates, thermal conductivity. Then you need to find the Reynolds number. Again, Reynolds number depends on the number of plates. So here you can use actually one equation to find the Reynolds velocities, and then you can find the Reynolds number. So Reynolds number is higher than 100. Both fluids are, turbulent. And then you need to find the overall heat transfer coefficient. To find the overall heat transfer coefficient, you need to find the Nusselt number. So, and then you can find the overall actually heat transfer coefficient, m dot Cp. The next step, you can find the exit temperature. Look, guys, my solution here is a little bit different from my PowerPoint file. Here, first I calculate the, exit temperature for clean heat exchanger. So I assume that we have a clean heat exchanger. So look, I just calculate the overall heat transfer coefficient by using the heat transfer coefficient for hot water, for hot fluid and cold fluid. Look, there is no term actually for for let's see, fouling factor. Also, guys, you need to add the term for the for conduction, but this is really negligible. Let's add it, and then you can see that this is really negligible. Look, this is the overall heat transfer coefficient without the conduction. Let me add the term for the conduction. So for the conduction, this is T. The thickness, where is the thickness? The thickness is here. Yeah, thickness over thermal conductivity of plate. So the thermal conductivity of plates is 14.3, but not 140. I will fix it. So this is, let's see, 14.3. Yeah, and then this is, the thermal conductivity, actually the overall heat transfer coefficient, for the, heat exchanger, for the clean heat exchanger, by using this thermal conductivity. So now Yeah, in this case, guys, I explain you, I just first calculate the exit temperature for the, new heat exchanger without using, those, fouling factors. So then let's see, then you need to check the heat balance. This is the heat balance. So to calculate the heat balance, you need to find the F and also NTU. F is, more than 0.75, 1 gram white. And then I calculate the R sorry, yeah, you need to calculate the lightning temperature difference, and also you need to calculate the QW, QC, and Q, and you can see that, there is a heat balance. And then the next step, you can calculate the outlet temperatures after 1 year. Now I just use, the fouling factors to calculate, the new overall heat transfer coefficient, correct? So, yeah, and then you can see that, the actually new uh, overall heat transfer coefficient is pretty close, to the previous one, correct? So yeah, again, you need to find R, AC, and then you need to can find the new, temperatures. You can see that this new temperature after 1 year, they are pretty close, to the, temperatures actually, uh, you know, for the, new one. And this is because of this actually small, fouling factors. And then eventually you need to calculate the pressure drop. So for the pressure drop, you need to calculate the fouling factors. And then here we can see that the pressure drop is less than 70 kilopascal in both two, actual influence. So I just share all these files. They are available on the Blackboard. And so that's it, guys. Thank you very much and have a great day.